In this video, I'm going to talk about the most important aspect of the wireless network, namely the RF characteristic. So this is very important to understand the impairment, wireless impairment, which we are going to do in the project. First, I'm going to talk about two characteristics of RF wave. The first one, it's called the gain. As the name itself suggests, this is defined as the positive amplitude difference between two RF signals. What that means? So I'll basically go into the next one. Next one you will understand. There are two types of gain. One is active gain and another is called the passive gain. Active gain is achieved by placing an amplifier in between an RF signal. You can call it as an amplifier, or you can call it as a signal booster or wireless repeater and so on. The main job is that the RF amplifier receive the incoming signal, they boost it by adding a gain, so which is normally specified as dB, decibels. It will just say that this will increase by 10 dB or it will increase by 3 dB or 5 dB. So if you look into any signal booster or amplifier, they will have the gain given in dB. Whenever I talk about amplifier, there are two types of amplifiers. One work on the analog domain. They don't care what the signal is. If you tell them that okay, just amplify the 2.4 gigahertz, then they will amplify every signal of the 2.4 gigahertz, including the noise, background noise, everything, then it'll just send it. So that means that your noise is also amplified. In the digital domain, they are called store and forward amplifiers, where the incoming signal is processed and it is being stored so that actual bits are recovered. Then these bits are then retransmitted. So it doesn't do it in an analog domain that whatever the signal comes in, it amplifies. So this one, they have the digital domain one, they have bit of a latency. So the entire packet is received, it will decode, then it will convert into a frame. If you call Ethernet, it's an Ethernet frame. Then it will repeat it. It will repeat it. So so that means that there won't be any error in the packet. So this would tip the diagram which explains. If you look into the leftmost one, this is the original signal. So what will happen is that if the original signal, as they travel along the wireless medium, they will just start lower. So look at it, there is a loss. So because of the loss, the signal start losing its strength. You put an RF signal amplifier, this will just increase the amplification. So that's typically called active gain. So active in the sense that there is a device which actually amplifies. The next one is also called passive gain. The passive gain is not theoretically a gain, but it is something that you intentionally do it to gain in certain direction. For example, you can use what is called a directional antenna. If you use a directional antenna, it will only focus your signal in a particular direction. So that means that it is not typically a gain, but whereas you only focus on a certain lobe, the other region, the signal doesn't go that much. This is similar to probably one of the example which I would just tell is something like you wanted to actually call your friend. He couldn't hear. So what you do is that you typically put your hand around your mouth, then you just shout his name. So what theoretically happens is that when you initially scream, your sound waves travel at almost 360 degrees so that it started losing its strength. When you put your hand in front of your mouth, so you create what is called a directional sound lobe so that it actually travels to a longer distance. So that's what it happens. So you know that they are parabolic antennas. Parabolic antennas, they are direction antenna, where it actually focuses the beam only onto a certain direction. So the opposite, now we are talking about the opposite. The opposite of gain is loss, defined as the negative amplitude difference between two RF signals. When we talk about a gain, we actually amplify if you want your signal to reach for a longer distance. Again, mind you, have it in your mind, if you are trying to amplify, you are trying to amplify the noise as well. So that means that sometime if you actually have more noise, then you are amplifying more noise, so your signal become unusable. Even though you amplify, it becomes unusable. So you need to go for a digital amplifier or digital domain where it actually receive the packet, store it, and then forward it. So it's called store and forward amplifiers. But they are difficult. They are not that simple. Store and forward amplifiers, it's in theory I can easily explain, but in practice they are very difficult. Then when it comes to the loss, loss is quite intentional or unintentional. So what do you mean by unintentional? A natural kind of loss. Whenever a signal travels along a medium, they start losing their power. So the moment they start losing the power, at some point of time, the signal becomes so weak that you would not able to detect the signal, or it is actually almost goes close to the noise floor. So you would not able to detect between the noise as well as the signal. So we call it as a path loss, which we'll look at it a little later. That's called unintentional loss. So that's typically going to happen all the time, irrespective of whether you are sending signal through a cable or whether you are sending signal through wireless medium. It doesn't matter. It's going to die at some point of time. That's a natural process. There may be a circumstances where you need to intentionally regulate by introducing some loss. This could be due to FCC regulation. So they say that, okay, you can't have more than this much of power in your signal, so you may need to reduce it by intentionally adding some loss. You must have seen in other places like airports, hospitals, where you are not supposed to use any wireless devices. So what they do, they create Faraday cage. That's nothing but something which protects everything from the wireless signal. So typically, like it introduces a loss. So this is by doing it intentionally. I'm doing intentionally that you don't get the signal. There are certain places, there are several places you can think of where they try to create Faraday cage type of concepts where you don't want to get any wireless signal. So they introduce this loss intentionally. So these two things, how it is related to my project. One is that gain. Suppose you wanted to increase the access point's range. So typically you are looking at an access point which is sending the signal up to 50 meters. You wanted to extend to another 25 meters. There are two options. You can put another access point. That's one way. Alternatively, are you thinking of a wireless repeater which can boost the signal and then send it to another 25 meters? This you need to look at it. This you need to look at it carefully, then evaluate the pros and cons. So that's typically for gain and extending the range. The loss, you wanted to actually, if two wireless access points are interfering and you want to reduce the interference, what you can do is that you can intentionally introduce some loss into the wireless access point. You can do that by power management. You can reduce a bit of a power, transmission power, so that you can create what is called a smaller cell size. The smaller cell size typically will introduce less interference or less co-channel interference, adjacent channel interference, and so on. This aspect, gain and loss, it is like an equalizer. You try to equalize to what you want at the end of the day. So what you do? Go and do a field trial. Go and do signal analysis. Do some site survey. Based on the site survey results, obtain your results, table the results, and see how you can use this gain and loss function to equalize to a state that what you want. Now I am going back to the very, very important characteristic of RF waves and what are their implications. I'm going to now talk about the problems. So far, gain and then loss, it's not a problem, but it is a characteristic which you can use to increase the range, decrease the range. Now I'm going to talk about some of the RF characteristics which can create wireless impairment. You have to be very careful about what impairment, how it causes. If you understand the dynamics of the impairment, you would be able to provide a better solution. The first thing comes about what is called reflection. RF waves are almost similar to light. Whenever it hits a smoother surface, which is non-absorptive, it will start reflecting the signal back. Typically, it's a changing in the direction of the signal. It's called reflection. So whenever a signal hits a smoother surface and which is larger than the wavelength that carrying the signal, that's a very important keyword. It can only, object which are larger than the wavelength can only reflect the signal. If it is smaller, it will just go through. It won't have any problem. Once it reflects, what happens is that the waves bounces back. By doing this process, it's not only it will bounce back, but there will be some sort of an absorption as well. Now I will talk about 802.11 specific information related to reflection. In wireless LAN, we are going to use two different bands. One is 2.4 GHz, another is 5 GHz. Now, once you know their frequency, you can calculate the wavelength. Suppose if f is the frequency and lambda is the wavelength, f lambda will be equal to c, which is c is the speed of light, which is 3 into 10 to the power of 8 meter per second. So based on that, you can calculate. If you know one, you can calculate other. If you calculate that, typically the wavelength would be between 5 to 13 centimeters. So the objects that are greater than 5 centimeter in size for a 5 GHz spectrum are 13 centimeter in size for 2.4 GHz ISM band. And if the object is smooth, it will basically reflect the waves. For example, if you are on a 5 GHz spectrum, anything which is more than 5 centimeter will typically reflect. In a 2.4 GHz spectrum, anything which is bigger than 13 centimeter in size and they are smooth, they will just reflect. So that means that what's going to happen, like you look at the door seems to be smooth and they are definitely bigger than 13 centimeter. That's going to reflect the wireless spectrum. If you are looking into tables, the tables actually they are bigger than 13 centimeter. So they are smooth as well. So they are going to reflect. If you look at the lab, imagine a lab, computer lab or your home environment where you got a lot of windows which contains typically glasses. The glasses, they are bigger than 13 centimeters. Your doors are larger than 13 centimeters. They are smooth. They are going to reflect your wireless LAN signals. They not only reflect, but some of the energies are also absorbed during the reflection. Now think about it. Is reflection good or bad? If you say that if it is going to be bad, how it's going to be bad? We will look at it a little later and see that why it's bad. There is another characteristic on RF wave which also causes impairment is called refraction. The refraction happens when the RF signal changes the speed and bend while moving through different media. So different mediums such as drywall, wood, plastic will have different refraction indexes. So if you're talking about anything, any material, the material will have refractive index. So the refractive index will actually help you to determine how much refraction happens. So the common cause of refraction include changes in the temperature, changes in the air pressure, existence of water vapor, and so on. I'll give a typical example. The refraction causes so much of a headache in an outdoor wireless environment. You must have heard about point-to-point wireless. So where between two buildings they put a highly directional antenna. Again, understand the keyword highly directional antenna. So highly directional antenna means that they basically have almost a lobe will be less than a meter in width. If you wanted to interconnect two buildings across a road, a freeway or anything, You can't dig something under the ground to run a cable. It is not possible to run a cable, then you put point to point wireless. When you design on a dry day, there are not much of a white water vapor, then you can have what is called the wireless line of sight. So you may able to get a clear signal, you may able to get a better signal. The moment if there is a rainy day, there are more water vapors. When the signal hits the water vapor, the water typically bend the wireless wave. Because of the refraction, the waves, rather than going straight and hitting from one antenna to other antenna, it will just escape the antenna, though go somewhere else. So that means that on a rainy day, you are not going to get a signal, or you may get a very poor signal. So this is a characteristic of a refraction. In a sort of an indoor environment, the refraction is there, but how much it's going to cost, you have to basically see. Can I measure it? The answer is no. You would not able to. There are no equipments which can measure how much is the refraction. But however, we are going to actually see based on the impairment study that okay, whether it causes a problem or not. So this is an example. This is little bit of the graph. So whenever the incoming signal hits a surface, it reflects. So the characteristic is that whatever the angle here, the angle of incident is same as the angle it which reflected. In a case of a refracted signal, if you look at it, some signals are reflected, then some signal pass by. If you look at this particular area, this is where the things start bending. It doesn't go straight like this, but whereas it bends. So this bending angle is related to refractive index of the medium. The next one is called diffraction. So this is diffraction is actually, in the case of a diffraction, it actually hits some sort of a corner, so that it is not actually, it's nothing to do with the refractive index, but when it hits a corner, it actually bends and then changes the direction. So that creates what is called a typical effect is called RF shadow. Look at it here. So this is an antenna. The signal start going. This is the wave front. So when it goes and hits this corner, so this is an L corner. So the signal started bending. So it bends and goes. So it creates what is called, if you look into this sort of building, this area is the RF shadow. Shadow in the sense like you don't get any signal in this area. The old wavefront is going in this direction, whereas the new wavefront is actually going in this direction. So this one typically, if you look at it, it just changes. This one bends. It bends the signal by hitting the corner. Then the wavefront started changing its direction, then causing RF shadow. This will be pretty much common in an indoor environment where even in your house you can find several such sharp corners where RF waves can hit, then start changing its direction. Now the next another one is scattering. Theoretically, even though we call smooth surface, no surface in the world is smooth. They have some sort of a homogeneity. So what happens? So like that, it's just tiny specks. Even though we call it, when we just touch it and then see that it's very smooth, but in reality, if you just observe them with a microscopic one, it's not smooth. Whenever a signal hits, it just scatters the signal. When we talk about reflection, here the reflection means it's only on a uniform surface. This one, it hits here, it reflects like this. If it hits the other place, it reflects. So the signal is literally scattered along into several such directions. Can we avoid it? The answer is no. You would not be able to avoid scattering. In reality, you will have more of a scattering rather than reflection. It is hard to, or it is impossible to have any smooth surface. So typically a uniform reflection is not possible, whereas scattering is an offshoot of reflection, where the scattered signals goes along several directions. It's not one direction of the incidence. This would be a serious problem, and indeed it's a very serious problem in any wireless network, whether it's indoor or outdoor, it's both got the same issue. The next important property of an RF wave is absorption. Whenever an RF wave hits certain object, the object absorbs the energy. We have seen the object reflects the energy, refraction happens, diffraction happens. In this case, any object also absorb the energy. So what are they? An example would be water, drywall, wood, even humans. Whenever a microwave hits a human, the human absorbs the microwave. This property is actually used in microwave ovens. The microwave oven use absorption principle. What happens in the microwave? It uses exactly the same 2.4 gigahertz spectrum. You use it for your wireless communication. However, they use a very high output power between 700 to 1400 watts, whereas the wireless LAN uses something like 30 milliwatts to 4 watts and so on. Whenever your wireless signal hits your object which is kept in the microwave oven, they start absorbing. Once it starts absorbing, then it will start oscillating the water molecules. Because of the absorption, it start oscillating the water molecules. Then it start producing heat. So RF signal here is converted into heat. So that start cooking your food. Being said that, a microwave oven can interfere with your wireless communication. They operate on the same frequency, so the microwave oven can interfere. So this is an example of some standard material. If you are looking into plaster board, which is quite common in every Australian walls, they absorb something close to 3 to 5 dB of signal. Glass and wall, they are almost 6 dB, metal door 6 to 10 dB, window 0 to 20 dB depending on the tinting, gas filling and so on. Concrete walls 6 to 15 dB, block walls 4 to 6 dB and so on. So that's the absorption rate. That is why if you are looking to design an indoor wireless in a concrete jungle, like if you are looking for a concrete apartments where you are designing an indoor wireless, it will be very difficult, because if you put some access point in one room, you may find it difficult for the signal to escape and come to the next room. That's because of an absorption due to concrete walls, which typically goes up to 15 dB, their absorption rate. If you got a signal power of something like 20 dB, it will absorb 15. So you will only start getting 5 dBs out. So that sort of a thing max you are looking at. Now this particular aspect tells you what happened, like what are all these impairment mean to me. We call it as a multi-path and delay spread. What do you mean by multi-path? If you got a transmitter which you send the signal, the receiver expect only one signal to arrive from the transmitter. Then that's easy. I decode it, then send it to the upper layer. In reality, this doesn't happen. The same signal hits different surfaces, reflected, refracted, then scattered. They come in a different time. One signal come quicker, which is in a straight line. The remaining signals come after certain time. They hit the same signal, the same bit. If you send one bit 1 and 0, then the first one will arrive certain time, then again the reflected one will arrive after a little bit of later time, then other one, scattered one, arrive at a later time, and so on. So this is something, even though you call it as a nanoseconds, think about the speed. You are talking about 100 megabit, 1000 megabit. In that case, the bit width is so tiny that even a nanosecond causes a lot of issues. This is called a multipath spreading. In RF, this is very much characteristic. Multipathing, you have to deal with that. There are several algorithms available to look into how to deal with the multipath and delay spread. In this one, what is important as far as the site impairment analysis, if you got too much of a multipath effect, you will have more errors. How to avoid multipath? Sometimes it's not possible to avoid multipath. If you got a glass doors, are you going to replace? Like, are you going to say that, look, I'm going to pull out the glass doors and put something in? No. Your engineering department or typically your architect is not going to be happy. So what to do? How to overcome that? You have to think of how to overcome that. Your design should consider a, probably a plan B, how to overcome that. So every impairment, wireless impairment I spoke before, they introduce severe multipath and delay spread. How you are going to tackle that, that's what the challenge in this project. Multipath, we are not probably interested in how to measure that. However, what I do is that the multipath introduces more of a noise. What I mean by noise, we only consider for certain nanoseconds that the signal is same. Remaining, if it arrives after certain for example, I give you a rough example. Okay, I'm going to consider only 2 nanoseconds. The signal which arrives within 2 nanoseconds, I consider as same signal. Anything which arrives after 2 nanoseconds, I'm going to consider it as a different signal. Then what if the same signal arrive after 2.2 nanoseconds? Then you consider as a different signal. So that means that it is the same frequency, same information, but it arrives 2.2 nanoseconds later. So that means that that signal is considered as something different. So that is going to interfere with your existing signal. So it causes a noise. So the same signal which arrives 2.2 nanoseconds, you call it as a noise. That's going to interfere. So you would not able to get the bits back. So that is why every RF characteristic or impairment which we have seen before, that's going to have the multipath effect. How to deal with that? That's the challenge. We are going to look at it. What next? We have seen RF characteristic, so you will have a better understanding of what are the impairments, how that's going to affect your RF signal. The next video, I'm going to look more into the survey tools. I'm going to talk about some of the freely available survey tools that can be used on your mobile phone or laptop to evaluate the existing network performance. You can deploy that anywhere. You just walk into any place, just open your tool and see how many wireless signals are around you, how they perform, and so on. This is an important starting point. Like, if you understand the survey tool and impairment, wireless impairment, you would be able to provide a better solution for the problem in very wireless network. Stay tuned. I'll be talking about the survey tool in my next video.